To recall some of our basic operation here, I just wanted to remind you that most voice over IP systems include a couple of different services or protocols. So here we have a small topology. You can see that there's an asterisk box here that is acting as our server and our registrar. And then we've also got a TFTP and a DHCP server. And then there's a couple of phones there. And the first thing that happens is that the phones have to get DHCP based addresses from somewhere. You can do this statically, but most people do DHCP. And then it's very common, especially for desktop phones, to go out and look for a TFTP server somewhere. They download the latest firmware, download settings files, things like that to tell them about the configuration for the network. One thing that they might pick up is where the call server is. All right, so that's to get us going. Of course, there's a PoE switch in the middle, and these things have nothing to do with voice over IP in particular, but they are part of many voice over IP systems. After DHCP and TFTP are finished, we now contact the call server, and in this case, we are going to use a new signaling protocol called SIP. Now, if you remember right, voice over IP is really broken down into two kinds of protocols. We have the signaling protocols, and then we have the transport protocols. Our three major signaling protocols are H.323, Skinny, and SIP. All of these use RTP as the transport protocol. So that's something we have in common, and we'll talk about RTP in another series of videos. But right now we're talking about the signaling protocol. Unlike H.323 and Skinny, we're going to go to port 5060 for SIP. And SIP has all of the familiar functions that we have with H.323 or Skinny. That is, we have phones that register. We have to find a way to contact other stations to let them know that we want to talk to them. So these are all things that are handled by our signaling protocol. So let's talk a little bit about SIP specifics. SIP is the Session Initiation Protocol. Well, what is a session? A session is when we are going to establish a transfer of voice data between two nodes. Really what we're talking about here is real-time data in all its forms. The most common is voice over IP. So when you set up a connection between two endpoints, really you have a session. Now SIP, unlike 323 or Skinny, is an RFC-based protocol. So you can pull down the RFCs anytime you like. They're IETF documents. And we're going to start with 3261. Now that is the sort of finalized version, although SIP has a lot of companion RFCs. And remember that the basic features and functions that we have here is being able to register with a gateway, being able to contact a remote node, find a way to establish the parameters for the call. These are all things that we're trying to accomplish with the signaling protocol. Now, H.323 has H.225 and H.245 to accomplish these two things. SIP has its messages or methods and also the session descriptor protocol that allows us to swap the parameters for a particular session. The basic parts of a SIP topology really include the user agent, and it has a couple of formats, and then proxies, redirects, and registrar server. Now the central part of this is the user agent, and this is really sort of divided up into two ideas, whether or not you're a client or whether or not you're a server. Now already we can start confusing things, but I'll just start with this way. Let's think about a call server or a call manager. This is typically going to be a user agent server, which means that it accepts requests from the clients and sends back responses to client query. The user agent client initiates those requests and then accepts responses from the server. Now, the tricky part here is that a device acting or using a UAS can actually be a UAC as well. Proxy is part of SIP topologies. Actually, it's part of a lot of topologies. The proxy here in this case is when you have calls that are forwarded on behalf of nodes or endpoints to another system or to another device. So this is what the proxy does. The proxy takes this call information or the invites and then forwards them on. It's not uncommon to see proxies used between systems. Now, another big part of SIP is the addressing that's being used. We're used to phone numbers, but SIP brings us into an era in which we use domain name services and email accounts and all that kind of stuff. So now we have something called the SIP URI, or SIP Uniform Resource Identifier, which is very similar to the email addressing that you're used to using. Now, this makes it much easier to contact and find other entities on the network. So we're used to saying, well, I want to send an email message to this person at this particular domain, and SIP allows us to do the same thing too. Now, that doesn't mean that you can't use phone numbers just like you use everywhere else, but there are a couple of other formats that we use. Now, one handy detail to remember is that when you're setting up SIP trunks, this is the format that we like to use. So you establish accounts on either side of the trunk, and then you forward those trunks to those particular users. And there are some examples of SIP addressing below. Now, these are some of the key SIP messages, or the SIP requests. Register. This is where you're going to contact the call server and try and log in or try and establish that you're part of the system. An invite is used when you're calling somebody. Trying and ringing are very similar. Ringing is typically from your own call server. Trying is, a lot of times we see this in between systems because the call server doesn't have direct contact with the called node or the other endpoint. And lastly, we have that session descriptor protocol that I mentioned earlier. It's actually defined in yet another RFC, and this is what we use to set up the parameters of the call. And SDP messages are actually wrapped up inside SIP messages. And here's an example of a SIP message. Here we see the header expanded, and this one in particular is called an options message. Now, if you look all the way down at the bottom of this, you'll see the allowed. These are all the methods that this particular endpoint or server is willing to support, and this one happens to be that options message. And we can see the type of system, you can see the port number used, and so as we go through the videos, what we're going to be doing is tracking SIP conversations using messages like this. But one of the very handy things about SIP, especially when you compare it to protocols like H.323, is that it's very easy to read. It's very simple to see what's happening. Last time we went through some of the SIP details, and so I didn't want to go on very much farther without talking about the session descriptor protocol, which is a part of SIP, or at least it's encapsulated in SIP. SDP is formalized in RFC 4566. And what SDP does for us that SIP doesn't do is describe what's in the call, what we're going to be using for the media session or the call itself. And that includes things like the media type and the codec. We'll take a look at a packet here in a second. Connection info such as the IP address. And then there's a session name, and it's just a name that we use to more easily refer to the collection of packets that constitutes the session. The duration, and there's actually a whole bunch of stuff in the SDP packets. Now, for those of you that are familiar with H.323, those types of calls start with H.225 to set up the call, and that's where SIP comes in. But to give us the information about the session itself, H.323 uses H.245, and that's kind of the place that SDP fits for SIP. So here's an example SDP packet. You can see there's an awful lot of information about the codec there, but there's also the IP address that we're using. There's our time description. And so this is the information about the call. If you take a look at the line that's highlighted there, you'll see audio 34008. That's actually the port that we're going to use. And so if we looked at the RTP packets that come up later on in this conversation, you would see that RTP is actually using that particular port for the conversation. Now, this is again similar to what H.245 does with H.323. It sets up the connection, tells us how we're going to drop out of our signaling protocol and into our transport protocol. So let's take a second and return to SIP. So we talked about some basic structure. SIP has, the to and the from values. SIP also has the call ID. This is how we identify all the packets that go along with this particular call. It has sequence numbers, the methods that are supported, SIP addressing that is used. Those are all part of the SIP packets, but I didn't show you yet the collection of packets that's used on a regular basis. So on this particular image, what we see on the top part here is a phone starting up. So we're going to see that the phone registers, swap some details about the supported methods, and then we return a couple of statuses here from both sides. Now the collection of packets below that, you can sort of see that the number changes. So you went from packet numbers 112 through 115. And then we had packets that were 10 through 25 here. And that's because we're looking at two different captures. They're from the same phones, but two different parts of the operation. So the first part is the phone starting up, finding the call server and registering. And then the second one is an actual call. And so in this case, 1.11 here has initiated the call, goes out to the call server and says, hey, I want to call this guy. So we can see that there's the invite that goes, and then the trying and ringing messages, and then we have the connection is actually made with the SIP or SDP packets being swapped to describe how we're going to set up this session. And then we drop into RTP, which is our transport protocol. Now the other thing that I'd like to point out here are those statuses or the codes. And so in these packets here, we can see the status of 100, 180, 200, and that's because we've got a couple of very common codes here, provisional codes, and then success codes, and I'll outline those a little bit for you later on. And in this image, you're just isolating those SIP packets that have something to do with the call. Now, what I also wanted to point out here is that a very handy tool in Wireshark and OmniPeak and other packet capture analysis software tools is the ability to flowchart the conversation. And so this becomes an important skill for us, not only in being able to read one of these diagrams, but actually be able to generate one. And so here we can see the two sides of the conversation, 1.1 and 1.11, and here are the messages flowing back and forth as indicated by the arrows. So this is who's sending the message to who and the codes that go along with it. And then of course we can see the RTP stream toward the middle bottom. And then lastly, we see a SIP message that we haven't actually talked about yet, and that's how we close down a SIP conversation with the SIP bye message, and then the acknowledgement coming from the other side. And these are the SIP codes here. I mentioned that the 1XX, those are provisional codes. We don't really know what's going on. There's not a real problem. We're just sort of waiting. We see this very commonly when nodes are trying to contact each other with invites, and especially when we're going across between call servers. The 200 series or the 2XX series, those are happy codes. That tells you that what you were trying to do worked. 3XX means some form of redirect, again, very commonly between systems. Anything that begins with a 4, 5, or 6, that's bad. These are error codes of some kind, and hopefully we can stay away from those. But if you're trying to set up a SIP trunk or something like that, and you're getting annoying tones in your phones when you're trying to call, it's likely that you're generating 4XX, 5XX, 6XX error code messages. All right, as we get ready to wind down today, I wanted to close up with SIP trunks and SIP security a little bit. SIP trunks are one of those things that everybody talks about. Sometimes they seem a little bit confusing, but if we take a look at what is referred to as the SIP trapezoid, this is an image right out of the SIP RFCs. You can see that I've tried to include all the reference information for the image, as I didn't make this one. We can see that there are two maybe call servers or proxies here, and we see Alice and Bob on the two sides there. So if you can imagine a system that Alice is residing on as having one particular set of dial patterns. So here at RIT, everything begins with a 475. And over there at Bob's phone, maybe everything begins with 777. So anytime you're calling from Alice to anybody in Alice's organization, it's handled by the local call servers. But when you're trying to call somebody outside, you've got to have sort of a gateway to send this to. And that's really what SIP trunks are all about. So Alice's proxy or Alice's call server recognizes that when she dials 777, it's destined for the network that Bob resides on. And so it's got to be sent to the other end of the SIP trunk, in this case, the Biloxi.com proxy. In the same way, when Bob wants to call Alice, he's got to dial 475. And so that dial pattern is being recognized as being part of Atlanta. So there are two parts to a SIP trunk. One is what dial pattern are you trying to reach? And then what is the account or endpoint that's associated with this particular dial pattern? And that's pretty much the nuts and bolts of a SIP trunk. If you are a networking kind of person, SIP trunking is not unlike static or default routing. So that's kind of what we have to do. We have to set up a dial pattern or a network pattern and send it to somebody, and then they have to figure out a way to send it back to us. Okay, SIP and RTP security. Well, if you were taking a look at voice over IP security, the two big weaknesses that we have are going to be in SIP and RTP, although for different reasons. SIP is very easy to read and understand, so that means the SIP signaling messages, such as registration, such as calls, invites, they're all very easy to spoof. And so SIP is susceptible to injects and hijacks and man-in-the-middle attacks. Now, as you saw from the packet capture, and especially if you've been reading the chapter, the SIP header format and the SIP fields are actually very easy to understand. So again, for an attacker, that makes it very easy to read. Now, RTP has a completely different problem. RTP, as you may remember, is the transport protocol. And so you encode the audio or the video with a particular codec and then send it across. And so if you just had the data, you would have no idea what it means. But RTP is very handy in that it tells you exactly what codec was used to encode this data, with G.711 being the most popular one. So that means that anybody that understands how a codec works and that has support for the codec that you used can be fed your packets and then replay them. So for those of you that are fans of Wireshark or OmniPeak, both of them have the ability to play back G.711 streams. And so that's the basic problem with RTP, is that you can collect RTP packets and then play them back at random. You can also inject RTP packets into streams by giving them the same values as the RTP stream and just direct them at the destination IP address. But the most common problem is